Hey everyone, thanks for joining us. I'm going to give everyone a couple seconds here to log into the webinar, and then we'll get started. All right. Well, good afternoon or good morning, everyone, wherever you're joining us from. Welcome to today's webinar, co-hosted by the New York Oracle User Group and Viscosity North America. And we've got an awesome Oracle Ace here today presenting for you. But before we get started and before we hear a little bit from NYOUG and Viscosity, I just want to tell you a couple little house rules we've got. So it is a live webinar, and yes, it's being recorded. And yes, you will have access to rewatch it either later today or tomorrow. And we'll also give you access to the slide deck as well. So thank you in advance to our speaker for that information that we'll be sharing out. Also, if you use the chat feature or the Q&A field here in Zoom, Q&A, that will go to Kai, our speaker today. So please, throughout the webinar, go ahead and put your questions in there for him to answer either along the way or he'll catch up at the end of his webinar. If you have logistical questions for myself or Coleman from NYOUG, put that in the chat section for me and we'll get back to you as soon as we can. So with that, I'm going to turn it over to Coleman, who's going to tell us a little bit about NYOUG.
Greetings, everybody. Thanks for attending this webinar, whether you're in the Eastern time zone or the Western time zone or another time zone around the world. New York Oracle Users Group is always having webinars for our meetings. And you can connect with us on Twitter, on Meetup, LinkedIn, Facebook, and our website. And we're always looking for speakers for our sessions. So you will get a lot of publicity that way by speaking for on your topic of knowledge on Oracle. And we look forward to future sessions with everybody. Next slide, please.
Oh, I think this is the only NYOUG slide I have.
Okay, that's the only one. Just as a summary, we've been around for, I think, close to 45 years, if I'm not mistaken. A long time. I remember that being true for the New York Oracle Users Group as far as the other president's concerned. So right now I'm going to turn it back over to Monica, and she's going to talk about viscosity.
Thank you, Coleman. Yeah, so if you guys aren't familiar with me, hopefully you are just from a lot of these webinars. My name is Monica Lee, and I'm the marketing director for Viscosity North America, where our mission is to enable business transformation at a time when companies must change to survive. And we are a full Oracle stack consulting firm with core expertise in Oracle database, including RAC, Oracle Apex. We perform a lot of near zero downtime migrations, performance tuning, anything with high availability. We've got decades of experience with infrastructure, including engineered systems. We do offer project-based services as well as managed services and training. And we've been upgrading many of our customers to Oracle Database 19c. We also host monthly workshops through orapub.com. On this screen, you'll see a couple of our leadership folks that are part of the Oracle ACE program. If you're not familiar with that, that's also what Kai is part of, and it's a distinguishment from Oracle for non-Oracle employees. And these people speak on Oracle topics around the world. They write and they help customers and users like you. So definitely check them out, follow them on Twitter. And yeah, it's a lot of great content there. This slide, real quick, just shows you a bunch of different services we provide. I'm not going to spend too much time here, but I do want to point out that we have several people on our team who used to work in Oracle license management for Oracle. And it's one of the big things that help our customers make sure they pay for what they need and they're getting the best rates they possibly can. And also, just getting a little bit of assistance there and in helping your team and maybe your management make the right decisions and take advantage of in your investments. That's kind of what we're here for. All right, over here, we've got a lot of, like I said, a lot of speakers within our management and our consulting firm. So this just shows some of the books they've written. It's a little outdated, but we've got like 20 something books under our belt, which is great. And then as of the 1st of 2022, we actually now have AuraPub with the Viscosity brand. So we say AuraPub is now powered by Viscosity, which is awesome. It was founded by former Oracle employee and current Oracle ACE director, Craig Shallyhammer. And if you're not familiar with him, he's another great speaker of ours. But this is your one-stop shop to find a bunch of webinar recordings, slide decks, even when they present at conferences without the webinar, we actually put their slide decks on aurapub.com as well. So you can still catch a lot of great free content here. There are paid membership tiers as well, but if anything, I recommend just signing up for free access, and you'll get things like today's presentation on there. If your company reimburses you, I definitely recommend getting a paid membership, but definitely check it out. And otherwise, before we get started and before Coleman introduces our speaker today, please check out events.viscosityna.com. Like and follow us on Facebook and Twitter and LinkedIn as well with NYOUG. And if you have any questions, feel free to email me at monica.lee@viscosityna.com. All right, all yours, Coleman and Kai.
Thank you very much, Monica. Kai is a distinguished engineer of Dell Technical Leadership Community and Dell Technologies. Kai has 28 plus years experience of architecting various IT solutions by specializing in various Oracle technologies. Kai is a frequent speaker at various Oracle conferences and has been an Oracle director since 2010. Just on a personal note, I remember Kai from many conferences from both Oracle World in San Francisco and also from Collaborate in Las Vegas. So we've traveled a few circles together, and I'm really honored to have Kai as a speaker for the New York Oracle Users Group today. Thank you again, Kai, and thank you, Viscosity, for this series of webinars.
Thank you, Coleman. Thank you, New York Oracle User Group, and also Velocity North American. Yeah, this is definitely an honor to have opportunity to share my experience. So shall I open my slide?
Yes, please.
Okay. Okay, I need to share first, right? Yeah. Hello, good morning, good afternoon, depending on where you are. Yeah, just as I just mentioned, it is an honor to be invited here to have opportunity to share this latest technologies. That's something I actually explored last year. I want to get this opportunity to actually show this technology. So many of us are DBA or developer. You may have experience with database performance issue. The one of the most obvious performance issue is actually I/O issue. So if you see some database that are moving, have very slow latency response time, and there's great chance that if you look at the AWL report, you probably can see the top weighting event. One of the top weighting event is I/O related. This is very common. Why? Because in the last 40 years, the hardware technology, such as CPU, has advanced a lot. And you can see, like right now today, you have a server can have many sockets. Each socket have many core, So for example, you can have a maximum like maybe a socket machine, or most common right now is 4-socket machine. And each socket you can have 28 cores. So literally if you time how many CPU, that's 4 times 28. So you add a lot of CPU, but this is just a Power equation. But database, most of intensive operation is I/O. But the last 40 years, the I/O storage has not progressed as much as the CPU. So that's why you constantly experience this problem. So you may get a very high power server. You pay a lot of good Oracle license, and hopefully you can run very heavy workload. But you know what? Your I/O will stop you, and no matter how many CPU you pay, or no matter how many Oracle license you pay, and your database is waiting on I/O, and your CPU is starvation. You waste your money, you waste your server money. You also waste your Oracle license, but you didn't get anything done. So that's why the I/O latency, I/O throughput is really critical for a database. So today's presentation is talk about a new technology that actually can tackle this kind of problem, can be one of the solutions. So yeah, as Kwame just mentioned, I'm actually working for Dell. I'm leading the Dell Oracle Solution Engineer team. This team actually covers the entire Dell the infrastructure, such as server, storage, networking, operating system. We use those infrastructure to build an Oracle solution, specifically for Oracle solution. We do have other programs support other workloads, such as SQL Server or SAP, but in my area is dedicated for Oracle database. So I've been working on all kind of technology since the early 90s. And recently I'm moving toward more to analytical or machine learning. So as Kwame mentioned, I also participate in a lot of Oracle community. That's where actually my passion is. So I've been admitted to Oracle ACE Director community in 2010. So I also have some book publishing. You can see the back to middle 2013 timeframe. I've been focusing a lot of time on Oracle RAC, but recently I'm moving even more on the more kind of emerging technology such as machine learning, AI. But the Oracle core technology is still my core competence. So I know we have a 1 hour, but there's a lot of content I want to cover. I think most of the people probably are not so familiar with the persistent memory because this is a hardware technology. And most of the DBA really don't much pay more attention to actually hardware server. But in this case, we do have to look at it. So I'm going to actually give a quick introduction about the persistent memory and also how we can leverage persistent memory for Oracle database. We're going to talk about 2 different modes that we can configure persistent memory. Each mode serves different purpose. One is the memory mode, one is the AppDirect mode. Now we look at how these 2 can be leveraged for Oracle database. What are the challenges? And why Oracle introduced this new feature to specifically support Oracle the AppDirect mode. Then I'm going to actually show one of the POC tests. Actually, I work with Oracle product team. So I actually got a chance to work directly with the Oracle product team that developed these 2 technology. We actually run an extensive performance test. I'm going to show some of the results. Then I also showed how the persistent memory using Exadata. This actually, I put XAM, actually it's also X9M. But then we're going to also look at the future. What is the future for that? So let's take a look at this persistent memory technology. So this screen just show this picture. This just show how the persistent memory looks like. So if nobody tell you what is this, you probably think this is just memory. Yeah, it looks like it's just like a memory, and also they also can be put into memory slot. So the form factor, physical form factor is just like a memory. But the way to access this device is just like memory called bi-addressable. So instead of SSD, you actually, or hard disk, you read the data by block. In this case, you actually read it by byte. This is similar to, exactly similar, it's the same as memory. This is actually co-developed by Intel Micron back to a few years ago. And when you use this memory, use this device, you actually plug this device into memory bus. So essentially, it's memory slot. And this table shows the comparison. So simply, this memory is like this whole hierarchy. And if you use a hard disk as one, you can see the persistent memory almost like 1,000 times faster. And the DRAM is about 10,000 times faster. But SSD is 100 times faster. And it also shows response time. And you can buy different capacity, 128, 256, 512. 512 is maximum. By saying that 512 maximum, and you only can put how many, because each server has a limited number of memory slot. So yes, you have a maximum limitation about how much persistent memory can have in each server, which we're gonna show a little bit more. Yeah. So far there are two generations of PMem, persistent memory. Oracle Intel put it called PMem. But Intel has this code name called obstinate. So yeah, but we just use the PMem. So we have a PMem 100 series or 200 series, and each one serves different level of the different type of CPU. And Intel also has a product name called Apache Pass. If you heard it somewhere like Apache Pass, that is 100 series persistent memory, and Bottle Pass is actually the 200 series memory. Those two are currently available on market, but Intel is actually working on the third generation. The Optane is their code name, the project code name. Product is actually the code name of the older product. But each generation, they also give them different name. So currently, the Core Pass is actually third generation, but I believe Intel is still working on that, has not released yet. This serves for fourth generation Exelon process. So, and this is how we just mentioned how this persistent memory actually plug into the server. This is just a logical exam, a logical diagram. So you have this CPU, what we call a socket, is actually a physical CPU. Inside the physical CPU, you could have many core. So in this case, I put a core, but you can easily get a 28 core. So in this case, when OS turn on, you actually can see the core. But when you open the physical server, you only see the one physical CPU. So beside the CPU, you actually have a memory slot, a memory channel connect to all the memory slot. So in this case, this is our Dell R750 server. Each socket has a channel. Each channel has two slots. So totally, each CPU, each socket has a 16 slot, and our server has two socket, which means we have total 32 slot. So besides this 32, they actually there's a maximum way to mention that. So this is actually the physical picture. So if you open the server, and those are the mount on the motherboard. So you have these two sockets. These are the memory slot. So all this memory slot belong to CPU 1. And all this memory slot belong to CPU 2. Internally they have a memory bus connected. So the maximum configuration is the recommendations you actually can if you want to. There are many different ways to configure. You could just not use PM. You put all memory in. So in this case, you will have all the 16 slot put a memory. In this case, you don't have a persistent memory. But if you do want to put a persistent memory, you have to do interleave. So one slot for memory, one slot for persistent memory. So in that case, totally I have a 32 slot here. So you can have by maximum, I can have 16. So I can have put a total 16 persistent memory into this server, because I total have a 32. I can use half of them for persistent memory, half of them for real memory. But if you do this, you have to interleave like one persistent memory, one memory. So in that case, if I use the most the 512 gig persistent memory, I can have total 16 times 512 gig. So totally 8 terabyte persistent memory. So remember this. This is a very important number. So each server, you can only have a maximum 8 terabyte persistent memory, but you can have less. So, okay. So when you put a persistent memory into a server, then rest of the things you have to think about how to use that. So you have two ways to do that. One is you configure, as we mentioned, the persistent memory. In the beginning, we mentioned that persistent memory itself is a memory, but you also can configure as a storage. So that's why if you configure this as memory mode, then this persistent memory will serve as a memory. This is called a volatile memory, which means when you shut down the power, all the data stored in persistent memory will be gone. But if you want to use the persistent memory to store data, then you have to configure the persistent memory in app direct mode. In this case, all the data stored in persistent memory, app direct mode, will be persistent, non-volatile. And when you shut down your database server, all the data is there. In this case, persistent memory will act just like an SSD. But one different thing is, as we discussed, all SSD or hard disk, they all access by block. So when operating system read the data or write the data, they actually use the operating system block, which is 512K block. Each time when they do I/O, they do 512K. But when we configure persistent memory, as an app direct mode to configure as a storage, then all the I/O when the operating system read the data from the app direct mode persistent memory, they're going to read it by byte. So it's not by block. So this could potentially create a lot of issues, which we're going to discuss later. And a dual mode is possible, but depending on server. Our server actually not allowed it, not official supported. Okay, let's take a look at how this persistent memory position in the storage hierarchy. So this is the line. Below this line is storage. Above this line is memory. The top line of memory is DRAM. So it's just like a memory. We use it. But persistent memory itself can be here or can be here. It depends on how you want to configure. So if we put a memory mode, then persistent memory is on this level. But if we configure as app direct mode, then will be used as storage. The one important characteristic is no matter what you configure, either memory mode or app direct mode, physically this persistent memory is actually plugged into a memory bus. That is very critical because all the other storage, no matter SSD or hard drive, they actually put a PCIe bus. The PCIe bus is much slower than the memory bus. So that's why the persistent memory itself, as we mentioned, is about 10 times faster than SSD, more than 10 times faster than SSD. But that's something we'll talk about storage immediately. But their connectivity to CPU is also much faster because they are using memory bus instead of PCIe bus. So that's the important part. So this is a PCIe bus. All the storage, no matter what drive we use, no matter how fast you drive we use, all plug into the PCIe bus. But the blue line are the memory bus, which allow them the faster transmit between the CPU and also between CPU or memory, between the CPU and also the persistent memory. Later, we're going to discuss the actual CPU can direct access persistent memory without going through the DRAM. That is a very, very important characteristic. And as we know, in the CPU, in the computer architecture, no storage, no CPU can direct access storage. They have to bring the storage block into memory first before the CPU can access. That is the storage computer architecture 101. But the persistent memory actually allows CPU direct access without going through the memory. That's called direct access. Yeah. So there are some studies that show that how they want to compare persistent memory with the NVMe and also with DRAM. So you can see that it's pretty close to DRAM, but it's much faster than this 26 response time. It's much faster than the NVMe drive. Okay, so let's talk about how. So if we already decided how do we want to use it, but you have to configure. So configure persistent memory has 2 steps. This is something all before the Oracle. So before Oracle can see it, so you have to make sure all operating system can see it. So before operating system can see it, you actually have to go to system BIOS to configure. So what this BIOS essentially does is actually group this. In this case, for example, I have like a 12 total. I have 12 PMem. So I create a region basically and kind of create a reconfiguration. Combine this. In this case, I actually created 2 zones. I combine this all in 1 zone. I combine this the left or the 1 zone, zone 0, combine the right in zone 1. So when you combine this, then this is something called region. Then the operating system, instead of see each call, they actually see the combined call. So for example, in this case, I have 6 times of each of this call. So that's important because by combining this, you also can make it faster, get a more capacity. When you do I/O, your I/O can spread into multiple calls. Just like when we do the reconfiguration of a hard disk. Okay, so let's talk about how the memory mode, how this 2 mode works. So if you configure persistent memory as a memory, then anything you have to do is come here, configure, make zoom them together, and then the operating system can see the two devices. So, no, this is actually this is probably already the. Sorry, yeah. So you can configure the app direct mode. In this case, it's an app direct mode. But if you just use the memory, then your operating system actually don't see this device at all. So this is app direct mode. When you configure the persistent memory as an app direct mode, then the persistent memory will zoom them together and become 2 devices, persistent PMem 0, PMem 1. But if you configure as a memory mode, then the operating system actually don't see this device. But instead, suddenly operating system will see your system memory kind of much bigger, because the operating system, when you configure the persistent memory as in memory mode, operating system cannot tell which one is DRAM, which one is PMem. Instead, they have this kind of operating system is smart enough to handle this, because this, when you configure memory mode, operating system also carry this kind of persistent memory drive to handle this. This is how it works. When persistent memory, when operating system want to retrieve data from memory, Then there's a memory controller. First look at if this byte, if it's in DRAM or not. But if this byte is not in DRAM, they go to the persistent memory to fetch it. But from operating system point of view, for example, in this case, we always recommend a 1-to-4 ratio. So for example, if your DRAM has 500 gig, then use a 1-to-4 ratio, I can configure a 2 terabyte memory. So in this case, in operating system will see 2 terabyte memory instead of 500 gig. So certainly you are seeing much bigger memory, the one of the benefit is you make this much bigger memory, but the cost, the persistent memory, I probably didn't mention earlier, but persistent memory is much cheaper than DRAM. You can make this much bigger. If you want to set a 2 terabyte memory, it's very costly, but persistent memory is much cheaper than the DRAM. But I don't actually have information about exactly the number, but because I did not do any sales. But my understanding is probably like a half or even less, maybe just a small portion of the cost of DRAM, and it's also much bigger because you can actually each car is much bigger. So what do we use it? So once you have so if you put a PMem configure as a memory, then your operating system immediately can see it. That is a great advantage because one immediate thing as the Oracle DBA, you will think about it, I can make my SGA bigger. I can make my buffer cache bigger, because currently one of the reasons that we cannot make a much bigger buffer cache is limited by actually how much DRAM you have. So theoretically, you should not make like more than 70% of your DRAM as your SGA. So if you have DRAM like 512 gig of DRAM, your SGA probably you definitely don't want to go above 400 gig, right? But if I can if I put a 2 terabyte persistent memory into a system, then suddenly I have my system memory become 2 terabyte. Then I can easily make my SGA 1.5 terabyte SGA. Then with that big SGA, there's a lot of things you can do. You can cache your database. If your database is small enough, you can cache your entire database. And by caching entire database, you simply you can limit a lot of I/O, because when you retrieve data, you're not going to retrieve data from the file. You directly retrieve from buffer cache, because your data is already there, so in the memory. Yeah, so you can keep your make your cache much bigger. You can cache your certain table space, and you can cache some index. So when you retrieve some data, you use index instead of go to data file to retrieve index block. Your index is already cached in a buffer cache, so that make a query much faster. So that is some good advantage of that. But one of the biggest advantage is for the OLAP type of application by leveraging the Oracle in-memory column store. So as we know, that in-memory column store is something Oracle introduced back to 12c to mainly supported a lot of BI or analytical reporting application. So they actually can build another set of memory instead of a buffer cache, instead another set of memory, use column format and store into the SGA. But you also have to look at it. All this is a part of SGA. So if your SGA is not big enough, you won't be able to build an in-memory column store. And a lot of time, when we do business analytical application, those databases tend to be much bigger than OLTP database. So you do want to cache as much data as possible. But in the meantime, your SGA consume physical DRAM. So you actually have this kind of issue. So you want to have a bigger in-memory in-memory column store. But other side, your SGA require a lot of buffer cache, which is very expensive because they all depend on the base built on top of DRAM. So by introducing this persistent memory, I can, as we just mentioned, we can make a system memory much bigger. We can make a SGA bigger. So potentially, I can allow you to build a huge in-memory column store. So for example, as we mentioned, I can give a maximum 8 terabyte persistent memory. In today's day, I am probably it won't be possible. At least I have not heard I can build an 8 terabyte DRAM, right? So it's going to be probably some machine may have, but 8 terabyte DRAM will be very, very expensive. But I can build an 8 terabyte persistent memory, put an 8 terabyte persistent memory, and also but with the 8 terabyte persistent memory, you can build maybe like a 6 terabyte SGA or maybe 7 terabyte SGA and give a majority of them to in-column store. So you can cache, can put all the entire big fact table into the in-memory column store, and this definitely help a lot. So we do have so I'm going to actually show some study. So people may ask us, if you put in-memory, if you use the in-memory as if you use the persistent memory to be to do the in-memory column store, do you have any performance issue? Because as we mentioned, in this case, we are pretend persistent memory is a DRAM because the operating system cannot see it. So when we do this, we also think we build an in-memory column store on top of persistent memory, but the persistent memory is actually a little bit slower than DRAM. So what can be any performance issue? Because then our lab actually did a study. I'm going to actually show some of the results. So we did a first study is with small database. We have two small database, and the one database we use all DRAM. We build an in-memory column store on all DRAMs because we have 700 gig, 768 gig DRAM. So database MCS only 300 gig. So definitely we won't be able to put it in. And persistent memory 1.5 terabyte. Both in this case, we use the same compression, and we compare, see what's the performance. In this case, the second database that uses persistent memory for MCS is a little bit slow, like 26% slow. So if we use 100 as baseline, so in this case, if we both can fit it, but what happens if we in this case we use a high compression rate, because if we use a high compression rate, then you will have big database, then the MCS image is quite small, in this case 300 gig. But if you use a less compression rate, like a query low, then suddenly MCS size becomes 960 gig. And 960 gig has no problem to fit into 1.2 terabyte, but they won't be able to fit into 760 DRAM because your SGA just cannot be big enough to hold MCS. Now what happened? So the database end up like split some data in your disk because you cannot build that. So majority of data will be stored in database. So when you run a query, you only read some data from MCS, but majority of data actually from disk. But for second database, I can read all the data from MCS. That's why the response time, query time is like much faster using PMem, persistent memory, because even your DRAM case, first database, your DRAM itself is faster, but the I/O part actually slow down everything. So that's the second test. The third test is we make a database bigger, and we use a bigger database, bigger DRAM. And in this case, first case is both use a high compression rate, both can fit into the database, and performance rate gap even smaller. But when we use less compression rate, and we pretty much repeat the same case, like because we use less compression rate. This 3 terabyte database has no way to fit into 1.5 DRAM, and because it didn't need like 1200 gig IMCS. So there's no way we can avoid I/O. So even we can 80% in IMCS, another 20% in storage. So in this case, the 20% data, the I/O slow down a whole lot. So you can see the almost response time for database 1 almost double as database 2. Database 2 is PMem, and we make use even less compression rate. Is very similar case. So in this this is the paper we actually published the paper. One from my colleague Naveen actually did this study, and we published the paper. So if you want to know detail, I can print this presentation. Actually gave you the link, yeah, so you can access it to show. So basically, this showcase that is perfect. Is a perfect match that use persistent memory to do the in-memory current store. In this case, you don't have to do anything. As long as your system admin configure the persistent memory in the DRAM, in the BIOS, then the operating system immediately can see it. You just assume you have, such big memory. You don't have to worry about it. What is data? Which part of memory is DRAM? What are the DRAM? What are the PMem? And you just consume. Think that this is just a huge big memory you can use on your disposal. Okay, so those are the big use cases for persistent memory, and we actually this study was done by joint with Dell and Oracle the in-memory team. So I think this paper also published in Oracle. But now let's take a look at another challenging part. So the persistent memory configures memory board. They solve one part of the equation, which is reduce the I/O. So because you can read the data, reduce the file, the database I/O, you can read the data directly from PMem. But they are part of a database. Certain part of it you cannot avoid. So for example, redo lock or database write. So you can keep the data in the memory, but if you have huge write, those write that need to write to database. So Oracle database has two fundamental write. One is redo write. One is data writer. Data writer is actually less because they do all batch. But the redo lock write is actually most troublesome because you have to constantly write it in the data. What we found was actually the redo lock writer. If you have very slow performance redo lock writer, you actually will experience this lock file sync issue. If you have high transaction database, you constantly update your database. If you put too much huge workload on a database, no matter how powerful your CPU, you will end up with this lock write sync issue, because simply, of course, lock write sync has a lot of other activities, but one fundamental activity is actually write your redo lock into the write your redo lock buffer content from buffer to actual redo lock file. But if your redo lock writer is not fast enough, and then you will see this lock file sync issue. So this is the extreme case that I see this system, because I actually run this database very heavily. So I end up like 11.5 millisecond redo lock write. This is, if your database see this kind of problem, your database simply stop, because you can see the DB CPU wait time is only 3.9%, which means your average, your query only spend less than 4% on CPU, but you spend a majority of time on I/O. So 71% on the sequential read, and 23% on the log file write. So when you have this problem, your storage stuck your database, and your CPU is not doing much. CPU is waiting your I/O. And even if you see this problem, no matter how much memory you put it doesn't help at all. So one idea was, can we make all this because your I/O is too slow, and the response time, I/O response time is too slow, because this I/O response time, this average wait is actually pretty much means the I/O storage response time. So each I/O you have to wait 12 almost 11.5 milliseconds. This is worst case. This number should be around the 1 millisecond level. So it's about 11 times slower than your case. This is 5 milliseconds. This also should be under 1 millisecond. So then we simply trace this problem back to storage. So how can we make this storage faster? So we already know that PMem itself is a memory. So their performance is 10 times faster than any SSD. So can we use the PMem to store data? So if you can use PMem store the read log file or data, then this weight should be reduced. This is our guess. Let's see what will happen. So yeah, so idea is we want to use persistent memory to store data, and hopefully this will cut all the response time. But let's see what the challenge is. Let's take a look at app directory mode. So in order for us to use PMem to store data, we have to configure the PMem as app directory mode. So there's a choice when you do BIOS. You actually have choice to make an app directory mode or memory mode. In this case, we'll select the app directory mode. So when we configure database, the PMem as app directory mode, there are few things happens. One is the PMem itself is bioaddressable, which means when you read the data from PMem, you're not going to read it by block. You read it by byte. Second thing is there's a potential that you actually operating system can read the data from PMem directly, bypass memory. They can read it directly. So in this case, the Oracle database, you have a buffer cache, you have a storage. In this case, when Oracle server process need data, potentially Oracle server process can directly read the data from your PMem without going through the buffer cache, without going through the SGA. So that's called direct access. But let's see what our challenge is. So first challenge is because the bioaddressable, if you use bioaddressable, but rest of Oracle's software treat the database as a block device. So which means the Oracle block device, Oracle database rely on operating system for any recovery, which means if your database, if your Oracle database doing I/O, especially read or write or data writer, you read block by block into operating system, then by byte. And if your server shut down, the Oracle rely on the operating system recover capability that you guarantee the last block, the 512K block, is atomic, so guaranteed recoverable. So even you shut down power, because your all SSD device by block. So every time you write, you either fail or not write at all. So because the unit is 512K, but app direct mode, PMem is write or read by byte, which means they only can guarantee last byte can one of the last byte can read, but the Oracle database think is a 512K byte, but your device only can guarantee 1 byte, which means your device could potentially lose 511 block. If your database I/O lost 511 block, your database will get corrupt. So that's why Oracle initially when this come up, Oracle only advocated we only can do persistent memory memory mode for database. Do not use this to store database file because they will corrupt database. So Oracle actually work on this silently. People may ask, what happened? I have a PMem. I have a PMem in the exit data. Why I didn't have the problem? Because Oracle, the way Oracle uses the PMem in exit data is totally different because they are in storage zone. The one we just mentioned is the PMem actually used as a local storage. We had an issue. But if your PMem uses storage server, you have all the software to handle all the integrity problem. So there was never issue with Oracle exit data using PMem. But using the PMem in the local storage to store data, Oracle was not like there's actually my support Oracle knows saying do not use that until July 28, 2021. So that's what last year. So Oracle released a brand new feature called 21C. Because first is called a database PMem database file store in 21C, released on August 13. So this case, and also the backport a lot of this into 19C. So 19C has to be 19.12. So patch set 12. And both of this guarantee, first issue is no corruption. So you can safely, if you use these two features, you can safely store database in the PMem without corruption. But only the 21C guarantee direct access. So 19C, the direct access was not there because I think there was actually patchy, because simply this Oracle, in this case, in order to use the direct access, Oracle had to rewrite a lot of IO module. And that was probably easy for 12C implementation than 19C. So both Oracle certified to use on both of this. So that's why I got a call from Oracle this feature also joined work with Intel. So last year, probably like September timeframe, I was starting working on that. So I actually did both. So let's see the PMem feature. The PMem feature I just mentioned that you can 21C is called 21C support direct buffer cache. So in this case, when your server process read the data, if data is not in buffer cache, they can directly go read it from PMem. In this case, PMem is not configured to for the buffer cache. PMem right now is configured as a file, the store database file. So according to Oracle IO architecture, so when server process need a block of a piece of data, they first look at the buffer cache. If that block is not there, they go to storage to get it. In this case, if storage is on PMem, they can go directly read the data. Previously, when you read the data, you from file, the data has to be a copy to a buffer cache first. Then server process can read it from buffer cache. But with this direct buffer cache mechanism, the server process directly read the data from buffer cache, direct read the data from PMem without copying the buffer cache, and then this will basically save time. But instead of a copy, they actually put a pointer in the buffer cache. So next time when the server process need the same data, they go to buffer cache. They're not going to read it directly from buffer cache. They will get a pointer. The pointer will point to the PMem to read the same piece of data. So that is called a direct mapping buffer cache mechanism. And the second is the guarantee no corruption. So this is actually how I probably didn't have time to go through detail, but essentially, that's how Oracle did it. So as we know that use regular file system, we have this problem called the corruption problem, also direct access problem. So to solve this problem, Oracle developed this new feature called file store. So essentially, file store is actually Oracle create a new file based on the DRAM and expose that file as a file store to database. So there's several steps. One is a DRAM on on the BIOS, you have to configure BIOS to zoom the different piece of multiple pieces of PMem. Then you create a namespace. In this case, it's just like a file system, like a device, operating system device. Then once you have this operating system device, then you use this. The Oracle gave you the command. You actually create a XFS DEX file system. So DEX file system is actually direct access file system. So you create DEX file system, then you expose this DEX file system to operating system. Then inside Oracle database, you create, this is actually in SQL command, you actually create a PMem file store. Once you create a PMem file store, then the PMem file store give you the mount point. This is actually mount point. U1 DB DB1 underscore PMem FS mount point. Just like our case, the U01 data. So then you can copy all the file, all database file into this. So think about all this is a mount point. You can copy all database file here, read log file here, all the control file, all the database file can put here. You probably noticed that this is a file system. It's not ASM. That is right. So if you use a PMem file store, the ASM is not supported. So this is just, you treat this as a file system. And the 19C is very similar. Also, but instead of instead of a DEX file system, this is not DEX file system. It's just regular XFS file system. So no direct access. So you actually do a similar way. You created this file system, and then you expose this to the Oracle database. Then you can copy all the file. But one part is you actually have to relink this file IO. So I guess Oracle basically recreate the OMS library. So this is actually part of all the new feature. So they replace some IO library that inside Oracle database. So that's why you actually have to relink the IO library to replace the previous version to get this support. So now you have this /Oracle OFS file system. Then you can copy all the file to that. And the rest of it is very similar to this. So you have this, you can migrate all the database file to here. But one of the kind of a drawback is you can create this file, but you may ask me, can we use this file, put into the DBCA so I can create database on top of that? But until that time, Oracle told me that the DBCA was not fully supported to use this file system. So previously, when you create database, you just tell DBCA where you want to put a file. Just give them the file mount point. Then DBCA will create database, put all database file under the mount point. But in this case, in this two file, that's not the case. So instead, you actually have to create database in a PMem file system. Just use any regular hard disk. Then you kind of migrate. After you finish that, you migrate your control file, data file, to this system. You can use the copy file, or you can use the RMAN to do that. Okay, now after we implement this, I actually did some studying. That's important. We spend all the time to implement this. Oracle spend all the code on this. Hold on, let me exit. So let's see if this new feature actually answer our challenge or solve our problem. So I actually run some very heavy workload on the database, which previously I showed you I got like a 12, almost 11.5 millisecond the response time. So I run the same workload, use this HammerDB. So HammerDB is kind of open source, TPCC-like workload generator. So I actually put a huge workload on that. I configure in such a way that we actually have 12,000 concurrent users hitting the database. Previously, the same database, I got like almost 5 million second I/O response time, and 11.5 billion millisecond the log passing response time. So I did this on the 12C, I think this 19C database. Yeah, it's a 19C database. Small. Okay. So now let's compare that. So the same workload, the response time previously was almost 5 milliseconds. Now it's 30 microseconds. So 30 microseconds equals to like a 0.03 millisecond. So if you think about it, this is probably like 100 times. So previous was 5. This was 0.03. It's like 100 times faster. 100 times faster the response time. And previously this number was 11 milliseconds. This was 81. So 81 microsecond, that is about 0.08 millisecond. Previous was 11. So you can see this is probably also more than 100 times. So same workload, just by replacing the storage medium, I was able to get it about almost 100 times faster in terms of I/O response time. As a result, the DB CPU time, so that's the average DB time, or the SQL, spend 97% of CPU. CPU got fully utilized because there's no much weight. There's no weight at all at the storage I/O. Everything is about storage, CPU. This server is very powerful server. It's a 56 physical core CPU. So if you do a hyperthread, it's 111, 112 logical core and 56 physical core CPU. Very high powerful CPU, and still, I was able to achieve a lot. And the throughput wise, so they also give us throughput. So this is actually 3 million throughput. Previously, I didn't show this number was like about like 400,000. So it's from 400,000 to 3 million. It's about 8 times CPU jump. So, and then I also added more user, continue adding more user. So the one I tested is 12. So this is I'm actually using hyperthread user. So each user is responsible for 1,000 concurrent user. So even I show 1,200 user is actually 120,000 users. So if I put a different user, the TPM increase, but the response time still not much. So still worst case is still less than 1 millisecond. So. And sequential read also still on under the microsecond level, and same. And the CPU utilization actually got a pretty high, 60%. So now I also run the same test on 21C. So 21C, so number very similar. Only difference is let's see DB sequential read. So when I did this test with Oracle want to see any like 19C or 20C difference. So they want to see the DB sequential read response time change, because in 21C they have DB they have this called direct read process. So or some transaction they the read can bypass buffer cache. So in theory, if you bypass buffer cache with this direct access feature, you actually can get a faster I/O. So we want to see the delta. So remember this one is 23.45, and the previously number was 19C number was 30. So I have this almost a 10% difference. No, 23, about no, actually 20-some% difference. So 23 to 30. That is the difference that was caused by the direct access. So Oracle actually initially told me that we should see more delta because you can bypass a lot of I/O. But my test shows that my test actually showed the gap was not huge. It's only like 20%. Then we went back to check that. Right. So I talked to Oracle why this number, because internally they tested their number is actually higher than their gap is higher than my number. So we go back to discuss. Then Oracle actually told me that so the internal mechanism to do direct access is actually not that straightforward. So let's see if database server process needed like block data. If that data is not in buffer cache, then they go to PMem to get it. Then Oracle actually later told me that depending on how the server process access data, if the data the server process retrieve is only for read, then they're going to bypass the buffer cache. So they just directly read the data, provide the server process, and give back to client. And then left a pointer into the a buffer cache. But if the read is for update, a lot of time when you have a SQL query, you actually read it, you also need to update a lot of time. For example, if you retrieve the customer information, you retrieve that. If the customer purchase something, you also want to update the row. So if that row is for update, not for read only, then the Oracle this process will be different. So they still need to copy that data into buffer cache. So here's the difference. If the data is read only, they're not going to copy. If the data is for read and write, they're going to copy. That is the later is the same as non-direct access. So that's why one of my test case is actually run huge transaction database. So the HammerDB is actually kind of a similar in the online store application. Huge update. So I would think like a majority of the I/O is actually read and write. So that's why the gap is not that significant, but still 20%. So a lot of time, if the data is on read only, they can take advantage of direct access. But if data like order information, and then definitely you'll read it for update, then they have to copy into the buffer cache. So that explains that the difference. Now people may ask me why this log file sync is huge. Previously it was 80. Why this 195? And later I actually did research. I found actually because the 23, because your DB file reader cache less weight, so the way this test case is if you have less weight, they're going to continue to add more workload. So then they end up a more update, huge workload, more update. Then if you have more update, you will have more log file sync. So you end up if you have more update, this will increase the workload on the redo buffer write. So you end up a little higher than the I/O wait time for log file sync. But still, you think I put more workload, but still quite small, and the majority are still DB time. So that is a test. Yeah, so this is actually the result. Very similar, a little bit higher than the 19C database. The add more workload, add more user, still not much change, and the response time is still kind of low. So I realized that this log file sync is get a little bit higher. It's close to 1 millisecond, but still much faster. Still like the regular storage is still like 11 times faster than this. Even I put a huge workload here, but most sweet spot is around this time swap. So if you get this, it's probably too much because I add too many users. Yeah, so very CPU, I actually push you CPU very high. Previously, I was able to, that server I was only able to get a 15% CPU utilization for that workload. After that's all IO weight. But now with the faster storage, I was able to push the CPU into 90%. Okay, so those are the studies that I have done for these two new features. Let's take a look at a quick take a look at it. How does the persistent memory used in the XDR platform? So this is actually architecture I got that from last open room. So what essentially the XAM, X9M does is they actually use the persistent memory, put in persistent memory in a storage server to store hard data. One of the hard data is actually read log, and and they also use RDMA. This is actually fast link. So from compute server, all the read log goes to this way, all the file goes to this way. So RDMA is based on InfiniBand protocol. It's got a much less response time and faster and more super. So that goes this way. And that's actually one of the reasons that by combining the RDMA and the persistent memory plus some software, that's the ingredient to get this 19 microsecond IO response time. You see that? So all of XDR is 90 microsecond. We are reaching almost 23. So we are actually pretty close, 23 microsecond. The difference is we don't have actually the secret source. So let's I want to talk about another things. Go back to the beginning. We mentioned that each server only can maximum have 8 terabyte persistent memory. So if we want to store database in the persistent memory, what happens if my database is bigger than 8 terabyte? So that is going to be a challenge because this is limited by the limitation. This is a limitation of the physical limitation. So one of the solutions Oracle recommended, I believe so, we also have some study with that, is actually combine these two architecture, sharding architecture and persistent memory architecture. Sharding is the way that actually a partition database, physical partition, not like a Oracle, there was like a partition table. This is different. Partition table is actually a partition table into different table space in the same database. But a sharding database is actually partition table into different database, physical database. We're talking about different storage, different physical server. And between the database, there's no much connection instead of just networking. So this is actually one custom table that depend on the custom ID, they actually distribute in 3 shard. And by taking advantage of the sharding, we can, if you have a huge database, like maybe 20 terabyte or 30 terabyte, so I can split that database into several small database called shard database, and put each shard database on top of persistent memory. So that is actually one of the, I know it's kind of complex configuration, but this is the way to actually deal with the limitation of the physical limitation of persistent memory. So personally, I have not done that, but that's I think that's the way that Oracle actually recommended. Okay, so before we conclude this presentation, I want to talk about it. We can discuss this future. What's the future? We discuss all the benefit of persistent memory. We show that persistent memory can really help in memory mode, can help database in memory mode or the epidirect mode. But there are some limitations. For example, as we mentioned, that size is a limitation. Of course, we know that sharding can help, but not every database can be shard. Second thing is that persistent memory doesn't support epidirect mode doesn't support ASM, and also doesn't support rack. Remember, persistent memory is actually the storage installed inside of a database server. No other database server, no other database in other database server can access that. So there's not shareable. So simply rack is not supported. So you can think about this is actually Oracle actually latest kind of it's kind of prototype to handle this kind of storage performance issue. And in the meantime, Intel and Micron actually developed this technology, so Oracle can develop. And we see that we see this, and we actually got a lot of good benefit for that. But certainly this is a limitation. So at this stage, I would think this is still infant stage. And also, in the meantime, Intel is already looking ahead to a next generation technology. They call it the XLX. So Computer Express Link. Oracle, Intel is working on that. So this technology will allow us the multiple CPU connect to multiple memory outside the box. So right now, all the CPU is deeply connected to memory in the same box. There's no way that CPU actually can access memory in other box. I know rack, people may argue, yeah, the rack node can access the memory in other rack server, but this goes through the storage server. But there's no generic actually hardware architecture that allows us to access cross box. So that's the actual Intel is actually working on that. But in the meantime, actually, or is for business reason, Intel actually kind of announced it in Q2 announced it. They're not going to put a further development on this persistent memory. One of the reasons was Micron actually dropped manufacture. So when Intel developed this, they actually work with Micron, and Micron actually manufactured this persistent memory. But Micron actually announced, I think it's last year sometime, Micron announced to drop this business. And Intel has no way, simply say this is the collaboration between Intel and Micron is pretty much on this side, on this specific technology is already in. So Intel announced that they're not going to do more further development, but except that they're still going to continue development on 300 series. So right now, Intel promised they still do 300 series announced for 4th generation Intel server, but they also still keep enough inventory of 200 or 300 server series PMem for all the users that in the world continue to use that. But they're not going to just make this active project continue to improve that, because Intel mainly want to jump to XLX, the Computer Express Link, and also I believe it's also for some business reason, Oracle, Intel dropped this. They actually take a huge loss on this. So this was announced probably like so this spring, back to this spring. But it's just Intel. But the rest of server like Dell, VMware will continue to support that. Will continue support customer who use persistent memory, including if they want to use this for Oracle database, and guarantee the inventory at least for 2 years. And you also have to look at it. Bigger one is the Exadata. So we just mentioned that the persistent memory is actually core part, one of the core part of Exadata. So I think industry probably will handle that. Continue use the make this available. Yeah. So that's whatever I know, and VMware still continue to announce the support for persistent memory. Or actually, VMware has paper to talk about actually use persistent memory for Oracle database. But for us, I know that the technology innovation still continue. So we should, this persistent memory just gave us the first taste of this memory technology, how much this memory technology can do for our database. So we expect that probably in the future, near future, some, especially some big company like AMD, Intel, they all jump into the XLX. So I would think, and Oracle definitely is looking at that too, and because they all talk to each other a lot, and so I would think in the future, probably soon, probably can see something that even better. But it's just something that we have to keep on, thinking, ready to accept it, any new technology, and yeah. So that is me, and so yeah. So today we'll talk about persistent memory technology and how Oracle database can take advantage of that in the 2 modes, and what are challenges, especially for Active Directory mode, because initially Active Directory mode was not supported due to 2 reasons. One is a corruption issue. Second is the DAX support issue. So Oracle, this newly released 21C solve both problems, but 19C only solve one. But the important one, because you all make sure there's no corruption. And we also showed that the study we done proved that the number was almost 100 times faster, but compared with other storage. And the other storage was SSD. So, and now compare it to hard disk. Compare this with SSD, this is 100 times faster. And we also talk about persistent memory. In Exadata, this is also tied to future. So the CX technology, and how, I don't know what's the Oracle plan, in future for the Exadata hard data platform. But yeah, that's something I want to share. I want to share what I know. Hopefully this is helpful for just kind of a technology update. Okay, yeah, I know I'm kind of out of time. Yeah, that's all I have, Monica. Yeah.
Awesome. Thank you so much, Kai, for presenting for us today. And thanks everyone who is able to stay over time. I know it's great information. So, if we've got the time to spend with Kai, we're going to take it.
Thank you.
Just a reminder to everybody, it is recorded. We'll send you some information on how to access the recording once it's rendered and uploaded. And then you'll also get an access to Kai's slide deck as well. So just keep a lookout for an email from either NYOUG or Viscosity, and you can find everything you need. If you've got any questions otherwise, please feel free to respond to our follow-up emails as well as needed. So thank you so much, Kai, for all of that. It's a great presentation. And thank you to NYOUG and Viscosity for providing today's webinar. Thank you.
Thank you everyone for participating. Thank you.
Thanks, Kai. Thanks, Coleman. Take care.
Thank you.